So just to recall from last time, we've been talking about geometric quantization. So trying to take a symplectic manifold and a choice of Hamiltonian on it and upgrade that to a Hilbert space with an operator. And well, we got partway to doing that. We said, okay, the kind of natural thing to do is to choose a complex line bundle whose connection with a connection whose curvature matches the symplectic form. Once you do that, then you can define an operator on the sections of this line bundle that satisfies the correct commutator property in relationship with Poisson bracket. Let me just remind you, the reason we need that connection is otherwise you won't get the right commutator. The curvature of the connection magically makes the commutator work out. And then you say, oh, no, that's no good. That's too big. So we have to choose a polarization, integrable Lagrangian subbundle of the complexified tangent bundle. So this is sort of at each point, we choose half the directions, but those directions can be complex. So this is a little bit weird. The thing I will sort of try to remind you is a complexified tangent vector is the derivative of a map of C into your manifold. So this is sort of saying like, you can either say that the derivative is 0 in some real direction, or you can say it's holomorphic along some plane. That's what the vanishing of a complex tangent vector would tell you. It would tell you that there's some map of C and that the pullback is holomorphic. And you can sort of mix these things, right? So you can either sort of go all the way in the real direction and just say half of the actual directions of the tangent bundle are 0. That's called a real polarization. Or you can sort of go all the way into the complex direction and say, okay, there's a map of Cn into my manifold. So a complex, an atlas for a complex manifold, such that you're holomorphic with respect to that complex manifold structure. And those are called Kähler polarizations. All right, and so having chosen those half the directions, either sort of in a real way or a complex way, we only consider sections that are parallel with respect to that. We have a connection, so we can do parallel transport along kind of all directions parallel to this polarization, and we want to get 0. So for Kähler thing, that's saying that you're essentially holomorphic with some issues about the curvature of the connection. And for the real thing, that's saying you're constant along the polarization. Oh, and then the thing we kind of got to at the end is, no, that's not quite right either. Because if we have a real polarization and we have a section sigma that's parallel along the polarization, now if we take the complex conjugate section, so what happens when I take a line bundle and I take the complex conjugate of a section of it? I get a section of a different line bundle whose transition functions are gotten by taking complex conjugate of the transition functions for my original line bundle. And if you think about the fact that our bundle is Hermitian, taking complex conjugate is the same as taking inverse transpose for unitary complex numbers. The transpose is kind of gratuitous here because I'm talking about a line bundle. I'm saying for a unit complex number, complex conjugate, and inverse are the same thing. So we obtain the dual bundle. If you take the dual of any vector bundle, the thing to do is take the original transition functions and apply the automorphism inverse transpose of GLN to those. So that gives you the dual bundle. And for a unitary thing, that's the same as taking complex conjugate. Okay, so if I take a section and I multiply it by its complex conjugate, I get a function. And if the original section was parallel along my polarization, the function that I get is constant along P. So if it's a real polarization, I'm a genuine function, which is genuinely constant along the leaves. If I have a Kähler polarization, that's saying it's a holomorphic function, which is also sort of cutting out half the directions, right? For a real polarization, this is saying there are like n independent directional derivatives that vanish. And for a holomorphic thing, that's saying I have n independent Cauchy-Riemann equations that I satisfy. All right, well, that's a problem because I want to integrate sigma times sigma bar and say that sigma is an L2 if that integral converges. Now, obviously, I'm not going to do that on M because it's constant along a positive dimensional submanifold. The integral is definitely not going to converge. So instead, I want to mod out and look at the leaves of the foliation given by my polarization, and I at least have some hope that my function is going to be L2 down there. But if I'm going to say my function is L2 down there, I'm suddenly in trouble because it's just a manifold, right? So the example we talked about before is if your symplectic manifold is the cotangent bundle of something, I end up with, and I take the vertical polarization, I end up with a function on the zero section. And if I just have the zero section as a bare manifold, I don't know what being an L2 means. So I need some kind of measure down there to actually define being an L2 and to define that as a Hilbert space. All right. So what I want instead is that sigma times sigma bar is a top form, or actually I'm going to ask for something very subtly different called a density on that leaf manifold, because that's something I can integrate without any reference to a measure. The difference with being a density is I don't even need to have an orientation to integrate a density, but we'll see that in a minute. It'll sort of come out naturally. So I somehow want sigma to involve some kind of square root of this top form bundle. I'll just note here, because P is Lagrangian, that means the quotient by it is canonically isomorphic to the dual space. So the tangent space to modding out by this Lagrangian vibration, sorry, the cotangent space to that is actually the same as the foliation, sorry, the polarization itself. So the symplectic form gives me a non-trivial pairing. So the symplectic form gives me an isomorphism from Pm to the tangent space at M divided by P dual. So this is something that you always have with Lagrangian subspace. You have an isomorphism to the dual of the quotient. And I can interpret that as the cotangent space to the leaf manifold. All right. So actually, if we're thinking upstairs, it's maybe a little bit nicer to think that we want to get a section of the top wedge power of the polarization itself. And that will sort of give me the right thing downstairs by this Lagrangian property. All right, so there are a few different ways to interpret what this is supposed to mean. This is somehow like, yeah, it was a little bit of a rabbit hole that I went down trying to prepare for this. It took me far longer than I should have for the amount of actual class that will be taken up by this, but it's sort of an interesting story anyways. So one way to do this is to say we want a thing called a meta structure. So let me talk about that a little bit in general. Might be interesting for you anyways. So just recall, if G is a Lie group, then its universal cover is also a Lie group. And the map down to the original Lie group is a central extension. So when I take the universal cover, pi1 of G, so in general, when you take the universal cover of a reasonably well-behaved space like a manifold, the pi1 acts on the universal cover in the original manifold is the quotient by it. Well, if you do this with a group, because groups are special, actually the whole universal cover is a group, and pi1 is a subgroup, and the pi1 action is just multiplication by that subgroup. You might ask, left multiplication or right multiplication, and the answer is either one, it's central. And it's exactly because somehow, like, well, you couldn't make a distinction between left and right multiplication, so it must be central. All right, so for example, probably the most famous example of this is if I look at SONR, the fundamental group there is Z mod 2Z. And I don't have a belt here to demonstrate this. The classic way to do this is, now I did it wrong. Anyways, yeah, let me not pull up the picture, but the thing to do is if you have a belt and you do a full rotation once, you put 2 twists in it. If you do another full rotation, you put 4 twists, and assuming you don't have to worry about interlocking your arms, you can untwist it afterwards. And so whether you have 2 twists or 4 twists in your belt, tells you like whether you've gone around a non-trivial path in SO3 or a trivial path. All right, the universal cover of that is the spin group, the famous spin group. Well, it turns out there's also a symplectic version of this story. And again, like depending on which source you read, there's a bunch of stuff about, like, do you want to look at SP2NR? Do you want to look at SP2NC? There's some complicated stuff going on here, but I think we'll be okay. If we think about SP2NR, we're only going to think about real polarizations for the story. You don't, what you need half forms for is much more subtle with the Kähler picture. All right, so SP2NR, that's a simple real Lie group, and it's going to be homotopy equivalent to a maximal compact subgroup. This is a general fact about simple Lie groups over R. For SP2NR, that's a copy of UN. And we actually saw this because we went through polar decomposition. So choosing a maximal compact, there's one for every compatible complex structure on R2N. And the contraction is you write your element of the symplectic group as a unitary times something positive definite, and then you gradually shrink down the positive definite guy. So the key point here is the space of positive definite things is contractible. All right, well, pi1 of UN is Z, and you can see this because UN, there's a map taking the determinant to U1, and the fiber of that is SUN. SUN is simply connected. And so, well, whenever you have a fibration like this, where one of the terms is simply connected, the other 2 terms have isomorphic pi1s. Yeah, when it's set up this way, that's actually true. So if we, yeah, I'm worried is that true in general? I should be worried about like pi2 or something, but it doesn't matter. That's okay. All right, well, anyways, it's true that UN has a fundamental group Z, and the way you detect what class in Z you have is you take determinant and you look at what the winding number around the circle is. There's a universal cover of UN, which is just SUN times R. And there's a corresponding universal cover of SP2NR, which is harder to think about. I don't claim to have a good kind of model of what this is, other than to just say, well, it's an element of the symplectic group and a path in the symplectic group joining it to the identity mod homotopy. All right. But we actually aren't going to want that full central extension. We're going to want to mod out by the even things to get a double cover. So this kind of abstract algebraic topology shows that the symplectic group has a unique double cover called the metaplectic group. Oops, I wrote the wrong exact sequence there. So this has a subgroup, which is Z mod 2. And if I mod out by that Z mod 2, I get the symplectic group. So whenever I have something like this, a central extension, here I have G twiddle, and the kernel is some subgroup K, a meta G bundle structure on a principal bundle Q, realized I shouldn't call it P because we're talking about polarizations. Oh, and there's one I didn't fix. Is a G twiddle bundle, so a principal bundle for the bigger group, such that when I take the quotient of that by K, I then get an isomorphism to my original bundle. So with a fixed isomorphism, this Q twiddle minus K, that's canonically a G principal bundle. I often find it useful to think about this in terms of trivializing your bundle over the open sets of a cover and then thinking about transition functions. So with my original guy Q, I can trivialize it. I get transition functions in G, and now I want to pick transition functions in G twiddle, which map down to the transition functions in G. So a metaplectic structure on a symplectic manifold means that, so being a symplectic manifold means that your tangent bundle can be written in such a way that the transition functions are in the symplectic group. So I should say, I mean, this is very standard stuff, but maybe I'll say it a little more carefully. So we sort of discussed that you can always replace vector bundles with extra structure by principal bundles for the group that preserves that extra structure. So the symplectic frame bundle is the set of, why is this always so much harder when I'm on Zoom? It doesn't like this when I'm just writing for myself. All right. So the symplectic frame bundle, this is pairs consisting of M phi. Here, M is a point in M. And phi from R to N to the tangent space at M is a symplectomorphism for the standard symplectic structure on R2N. And so this picks up an action of sp2r by pre-composition. You can also think of this as choosing all possible bases in your tangent space where the symplectic form has the standard structure. So picking a basis of E1 up through En, F1 up through Fn, such that you have the standard inner products. Of course, that's the same thing because those are just the images of the unit vectors in R2N. All right, cool. So I have this symplectic frame bundle, and I can ask, well, that guy somehow built out of transition functions in the symplectic group, right? If I sort of cut my symplectic manifold up into small enough open sets, I can choose this isomorphism with R2n as an isomorphism to the trivial bundle with the usual symplectic structure. And then the functions on the overlap that relate the two trivializations will be transition functions in SP2n. All right, I can ask, can I lift those up to the metaplectic guy? Of course, we could have a long discussion about exactly when that happens. It's when the Stiefel-Whitney class, the second Stiefel-Whitney class, vanishes if your manifold is orientable, which it always is for a symplectic thing. But let me just say, this always happens if you have a real polarization. So having a real polarization is actually a pretty strong condition already. And in particular, it tells you that this first Stiefel-Whitney class vanishes. I think maybe I need that the vector bundle given by the polarization is orientable. But it's okay. Point is, it's not actually that big of a restriction once you've loaded on all the other restrictions of the geometric quantization anyways. All right, so this metaplectic structure, this is useful in part because it's kind of a single global structure for the manifold. But then on any polarization, it induces a different kind of meta structure. So let me not go through kind of all the arguments with the groups, but if you have a polarization, then you can look not at all symplectic frames, but at all symplectic frames where the vectors E1 up through En span your polarization, and the other ones, well, they go somewhere else. And that gives you a further reduction of structure group. And using that, you can show that this polarization also has a meta structure. And it has a meta structure for this extension involving the metalinear group. And again, you know, there's some discussion about, like, do you want the complex metalinear group? Do you want the real metalinear group? But since we're talking about real polarizations, this is the real metalinear group. And this is a little bit funny because it's, now this is actually a topologically trivial cover over GLNR. But it's not trivial as a map of groups. So what this metalinear group is, I have an element of GLNR. I should just emphasize, since there's complex numbers running around, I really mean GLNR. And a complex number Z, such that Z squared is the determinant of A. So now note here, of course, if the determinant is positive, Z must be a real number. If the determinant is negative, Z must be a complex number. But you're still getting an interesting group theoretic cover because now, for example, the identity matrix has a fourth root, right? I can look at
Does the maximal compact of this end up being spin C by any chance?
No, it can't be.
Okay.
Right, because the maximal, like, it's not topologically.
Oh, because it's just going to be O. It's just going to be O.
But the maximal compact of this is write exactly the same thing, but write A and O of NR.
Sort of reminds me of spin C. Anyway, okay.
I mean, the connected component of the identity of this is the connected component of the identity in GLNR, where you always take Z to be the positive square root of the determinant. right? So all of the interesting stuff here is the fact that this guy is like not connected, and the way it sits in the symplectic group. All right, so if I have a metalinear structure, I can define a complex line bundle associated to the EREP, where I act on a complex scalar by Z inverse, or I could take Z conjugate and Z inverse conjugate, and those are all different. None of those are the same representation. And so I can define half forms by taking the associated vector bundle for either Z, the action of Z, or Z inverse. So this is a representation that doesn't make sense for GLN R. Because if I have negative determinant, and I want to act by square root of that, you say, well, which square root? So exactly what this metalinear group does is it decides which square root you want. All right, so the correct thing to do, or at least one way to correct this issue about wanting to get a density, is to take sigma to be a section not of the original bundle L, but of L tensored with this half form bundle for P. What I'm saying here is that P has some transition functions, which I consume are actually in the metalinear group. And then I can take those same transition functions, have them act in this representation where the only thing you look at is how does Z inverse act, and take the associated line bundle. And of course, this tensor product is over C. All right. So if I take sigma times sigma conjugate, so sigma conjugate, that's a section of L dual tensored with not the dual of the half form bundle, but the complex conjugate of it, because I'm not assuming that Z is a unit complex number. It might not be because the determinant might not be. I'm getting the conjugate action, right, by Z conjugate inverse. So when I multiply those two together, I get a section of the associated bundle where I act by Z times Z conjugate inverse, Z conjugate inverse, which is the absolute value of the determinant inverse. So the bundle where I use those as my transition functions, so the absolute value of the determinant, that's exactly the term that shows up when I change coordinates in an integral. So actually, since the transition function here is the absolute value of determinant, I get what's called a density. This is something where there's a sensible integral, even over a non-oriented manifold. It's a strange beast.
Sorry, quick question. Would you mind just explaining, because you have a section of two different line bundles here, and then you write that the product is a section of, can you just say exactly what you mean by when you multiply sections of two different bundles like that? I think you
sure.
said it, but if you could just repeat it.
No problem. So what do I mean when I write that product? I mean that I think about the section sigma tensor sigma bar in sections of L tensor L bar this half-form bundle, tensor its conjugate.
So you tensor the two line bundles together first, and then you get an obvious section of that.
Yeah.
Okay.
So, right, a section of the line bundle and a section of its dual, I can pair those together and get a function. Right?
So there's a canonical map from this crazy bundle you wrote to just functions?
To densities. I mean,
to density.
So, right, the whole point was to not get a function, was to get something I can integrate.
Oh, right. Okay, yeah, right. I guess I'm a little confused by this last isomorphism.
Okay, so this is...
Maybe it's just it's just, how do you get from a map from a pairing of those two, what are those bundles associated to the metalinear structure?
Yeah.
To
okay, so
line bundle. Yeah.
How do we think about this? So, right, physicists, when they talk about this stuff, they talk about how does your function or whatever you're defining, tensor, transform under changing coordinates. This is sort of always the language that physicists use. And the way to kind of translate that into math is to say, when you take I'm starting with some principal bundle, what representation of the group that appears in my principal bundle am I taking the associated bundle for?
Mm-hmm.
Right. So for example, right, physicists will tell you, oh, a vector transforms this way and a one form transforms this way. Right. And what they're secretly telling you is
these are all associated to the frame bundle of the tangent bundle by different representations, right?
So start with the frame bundle. If you take the usual representation of matrices, you get vectors. If you take the representation of matrices on vectors where you multiply by the conjugate, the transpose inverse, then you get the dual representation, right?
So it's like, I see. So in this case, we have the bundle that these are associated to are like, we have two copies of the metalinear group, and then they're associated by this thing where you take Z. I'm sorry, I'll let you talk.
Yeah, that's fine. So yeah, I mean, if I have a section of this bundle that looks like, A1 tensor A2, right? And I transform this by, change. So I've chosen some trivialization of this guy over some open set. And I change my trivialization by multiplying by the element AZ, then I get Z inverse A1 tensor Z conjugate inverse A2. Oh, I'm tensoring together two things and multiplying them by scalars. I can just multiply the scalars together. Times A1 tensor A2. Oh, that's absolute value of determinant of A. And hopefully I've gotten all the inverses in the right place. I apologize if I screwed them up somewhere. And so exactly what this is telling me is these guys define a density. Because this is exactly the factor I would want to multiply by to say, no matter what coordinates I use, the integral of this guy over an open subset is well defined. All right. So it makes sense to integrate sigma times sigma bar over this leaf space, and I can at least ask whether it converges. If it converges, then I say that sigma is in L2. All right. So unfortunately, like so many of the sources I was reading from, they kind of get to this point and they're like, oh, we actually define metaplectic things. Okay, we can go home now. But one sort of example you'll see a lot is that you can take R2 with its usual symplectic structure. Its tangent bundle is trivial. So it just has sort of the stupid trivial metaplectic structure. And then I can look at these, the polarization by circles coming out from the origin. So that isn't well defined at the origin, but look at the polarization of circles coming out from the origin. This was something I was sort of tempting to use to try to understand the harmonic oscillator. But we have to pay attention to this metalinear structure. And I think this is one of these things where, I don't know, no source I read really explained this extremely well. But the way to think about this is, as you go around this circle, you want to keep trivializing the symplectic, the tangent space, the symplectic manifold, in such a way that one of your vectors, right? I mean, in this case, I'm choosing a basis, which is, yeah, just choosing a basis symplectically. And so I keep this trivialization going so that one of the vectors always points along this circle. Right? This is sort of the right way to get this metalinear structure. And so if I think about this, as I go around this circle, well, I make a loop in the symplectic group from the elements of the symplectic group I use to send my original frame to the one going around. And that loop in the symplectic group is not contractible. I go around the U1, I could just use the U1 inside SP2R, and I go around that exactly once. So this is a path which doesn't lift to a closed path in the metaplectic group. So what happens in this case is that the half forms are not a trivial bundle. They're the bundle where when I go around the circle, I glue by -1. So the real version of that is the Möbius strip, which is all a long way of getting to, I had talked before about, if you just kind of naively interpret this, you get that you have trivial holonomy around this circle if the x, oh, whoops, that's the, I'm just worried that do I have that pi in the right place? No, sorry, and then h bar. So I get trivial holonomy when a over h bar I is an integer. But physically, we know that's not correct. Those aren't the energy levels of the harmonic oscillator as you calculate it in quantum mechanics. And it's exactly fixed by adding a minus sign here. So the holonomy, and that minus sign exactly comes from the half forms. The fact that if you take a half form and you translate it around the circle, you don't come back to the original guy, you come back to its minus. So when you do this, look at the values of A where this guy is an integer, or is the question is this guy in 2 pi times the integers, 2 pi I times the integers. Got that right? No, sorry. Screwing this up. What I want is this guy equal to 1. So that happens when Let me just actually write this out. A over 2 pi I is in 2 pi I times the integers plus a half. Keep writing pi when I mean h bar. So I get that I should have A is 2 pi I, 2 pi h bar over times n plus a half, 0, etc. This is sort of the first interesting place where you see this metaplectic correction. There's another interesting place it shows up. Maybe I'll pause here for a moment. Are there any questions?
That's amazing. I wanted to say that.
All right, I'm glad you enjoyed. There's sort of another way to see where this half comes from. So I talked about the harmonic oscillator in terms of the Siegel-Bargmann space. And I had kind of unmotivatedly said, oh, there's this plus half here. And secretly where that comes from is you aren't just differentiating functions. You're applying Lie derivative of z dz to a half form. So to f, and in this case, you can write it as square root of dz. And if you just sort of naively interpret what that means, well, there's a term which is z df dz times square root of dz. And then you think about, okay, how do I take the derivative of a square root? So you think about like, oops, if Lie derivative is compatible with multiplication. So you think about what it means that the Lie derivative of this guy squared is 2 times this guy Lie derivative with respect to x of this guy. All right, you'll get the usual rule for differentiating a square root. So we get 1 over the square root times the Lie derivative of dz, and then a 1/2 because of the 1/2 in the square root and the chain rule. This term is just 1. Sorry, this term is just dz. So this term involves the divergence of the vector field, but you get a half. You get sort of a compromise between the formula for how you would act on a function and how you would act on the top one. All right. So somehow there are lots of like halves running around this metaplectic correction explains. All right. Everybody doing good? Okay. There's one other example of how geometric quantizations that I thought was kind of worth talking about. To simplify my life, I'm just going to say h bar equals 1 throughout. So if I start with a Lie algebra, then as we discussed, its coadjoint orbits have a symplectic form on them, and the action of G adjoint, the adjoint form of the group associated to G, acts on these coadjoint orbits Hamiltonianly by just including the coadjoint orbit into the dual of the Lie algebra. All right, well, the quantum operators also satisfy the relations of the Lie algebra because the Poisson bracket satisfies the relations of the Lie algebra on linear functions. So the Hilbert space is a representation of this Lie algebra. And kind of philosophically, there's this thing called the orbit method, which is that roughly you should be getting a bijection between representations of G and coadjoint orbits. And you should be very careful about how you interpret this fact, but this is kind of roughly true. So famously, this works surprisingly well with nilpotent Lie algebras. So let's recall the example of the Heisenberg. What do the coadjoint orbits of the Heisenberg look like? Well, it has this central element C. If C is 0, so C gives me a function on the dual of the Lie algebra, on the plane where it's 0, every individual point is its own coadjoint orbit. The coadjoint action is trivial. And when C is non-zero, I get a full plane's worth of translates. The Heisenberg acts transitively on all non-zero levels of C. And it turns out that you can connect these very easily to representations. So these 1D, the points correspond to one-dimensional representations where you set C is equal to 0. And so you get all possible representations of R2. So just all ways of sending X and Y to any scalar you want. That's a perfectly good representation of the Lie algebra R2. And on the other hand, I have these full planes. Those correspond to infinite dimensional representations of the Heisenberg, where C acts non-trivially. So there's a theorem called the Stone-von Neumann theorem that if I fix a non-zero value of C up to kind of completion, there's only one representation of the Heisenberg with that scalar. And that sort of comes from, you can actually see that now, we know, comes from L2 of R. It's the representation on L2 of R of the position and momentum operators. And indeed, while these 2D orbits as symplectic manifolds, they're just R2 with a multiple of the standard symplectic form. So you just do the sort of quantization story we did before. All right, so that's sort of one perspective on this stuff. And then there's the opposite extreme. So I could instead take a compact simple group and look at its Lie algebra and look at orbits in its Lie algebra. So the kind of classical example of this is SO3, or in the level of Lie algebras, that's the same thing as SU2. In that case, you're just looking at R3, and the coadjoint orbits are spheres. First thing to think about, when are they pre-quantizable? Right? Now that I have non-trivial topology, I always have a non-zero second homology class for my symplectic form, except at the single point. That's okay. So when am I going to be pre-quantizable? Well, it's when the integral of my symplectic form, So I'm in H2 of Z if the integral of my symplectic form over the 2-sphere is Z. But there's this factor of 2 pi that showed up. So I'm pre-quantizable if the integral over my coadjoint orbit is in 2 pi times Z. And you can actually do the computation of this. I had to do it myself just to make sure I wasn't screwing things up. So this symplectic form, remember you can think of SO3 as R3 with a cross product as your Lie bracket. So you can think of the symplectic form at a point Z in R3 as take the cross product with 2 orthogonal vectors, which are thus in the tangent space to the orbit, 2 vectors that are orthogonal to Z, to V, and the symplectic form is the cross product of those guys dotted with a V. All right, so you can calculate that what happens here is if I start at one unit vector times a scalar c, look at the other two unit vectors times that same scalar. So I'm also scaling those unit vectors because I want to make all of the different coadjoint orbits isomorphic to the one of radius 1 using the multiplication map. And I want to think about under that isomorphism, how does the symplectic form change? Well, if I go through this calculation, I find that I get the usual area form times C. So somehow I have to think about this, but yeah, you can go through, you can check I did the calculation right here. So what this shows is that the orbit, which is distance c from the origin, if I then make that isomorphic to the unit sphere using multiplication by c, my symplectic form is the pullback of c times the standard symplectic form on the unit sphere, so the standard volume. And so the area of my coadjoint orbit, distance c from the origin, is 4 pi times c. So I get pre-quantizable if I'm half integer distance from the origin. Which again, you know, somehow out of this physics, this maybe is not so surprising. If you go through what all this means in terms of connections, you can think of S2 as CP1, and the pre-quantum line bundle, if I'm distance n over 2 from the origin, is O of n. So my Hilbert space, I want to use the, forget whether I actually said this. So I found my pre-quantum line bundle.
Right. O of n is just the nth tensor power of the tautological bundle?
I think it's the dual tautological bundle.
Okay. I see.
I mean, the right way to think about it is it's the bundle whose holomorphic sections are homogeneous polynomials of degree n.
Okay.
And the reason it's the dual tautological bundle is, well, I think it depends which version of projective space you're thinking about, right? But a section of the tautological bundle, which is the line over the point, right? That's choosing a line in a holomorphic way at every point.
Mm-hmm.
I can't do that, right? Whereas the dual tautological bundle is the trivial bundle C2 mod the tautological bundle. And that has sections coming from the two sections of C2. Let me actually finish the sentence.
So
Kähler polarization.
is O of minus n dual to O of n?
Yes.
Okay. Thanks.
So O of n, this is the complex line bundle. The complex line bundle. Whose fiber at L is C2 mod L to the nth tensor power. And that's exactly why a homogeneous degree n polynomial defines a section. So any element of C2 defines a section of O of 1, and so any product of n of those defines a section of O of n. use the Kähler polarization. So my Hilbert space is the holomorphic sections of this bundle, which, as I just said, that's the degree n homogeneous polynomials in two variables. And indeed, that is a full list of the finite dimensional irreps of SU2. Every finite dimensional irrep of SU2 is defined by look at C2, that has the obvious action of SU2 on it. Now take degree n polynomials for some n. That's all the representations of SU2. And these factor through SO3 if n divided by 2 is an integer. Another kind of interesting thing to note is that the dimension of this space, it's n plus 1. So it's pretty close to being proportional to the volume with respect to the symplectic form, or more generally for the Liouville measure. And this is a general fact. So in this case, it follows from Riemann-Roch applied to P1, but there are generalizations of this in higher dimensions. All right. Are there any questions about this example? So actually, this is one of these sort of general facts about simple compact groups. If you know how to do it for SU2, probably you can figure out how to do it in general. So every coadjoint orbit for a compact group inherits a complex structure because it's actually a homogeneous space for the complexification of the group. And coadjoint orbits are always Kähler. You can actually find this, we had this discussion about Nam's equation for constructing hyper-Kähler metrics on the complex groups. Well, you can actually write the coadjoint orbits for compact groups as infinite dimensional Kähler reductions and get their Kähler structure that way. So a coadjoint orbit being pre-quantizable, what we saw in SU3, it was sort of about your distance from the origin being integral. And there's a sort of general version of that, which I don't think I want to get into in detail, but for example, for SUN, it has to do with the difference between the eigenvalues being integral. But once I pick out those pre-quantizable orbits, every finite dimensional irrep of G, and because of compactness, every irrep is finite dimensional, is the Hilbert space with respect to the Kähler polarization of a unique integral coadjoint orbit. And the symplectic form on the coadjoint orbit tells me what the representation is. So, I should say, as complex manifolds, almost all of these are isomorphic, right? So we saw this with SO3. There was one weird one at the origin, and then all the other ones were all just copies of CP1. So as complex manifolds, they're all the same, but we're choosing different Kähler structures, different symplectic forms, and those different symplectic forms give me different representations. And this is basically the symplectic way to state the Burrell Va theorem. So there's a version of this where you think about algebraic geometry, and instead of the symplectic form, you think about the line bundle that gives you whose curvature is the symplectic form. That corresponds to the embedding and projective space coming from take your representation and projectivize it. All right, cool.
So could you remind what the Burrell Va theorem is again?
It's basically this theorem. If you go look up what the Burrell Va theorem is on Wikipedia, I haven't actually done that, but I assume what it'll tell you is basically that every irreducible finite dimensional representation, they'll probably say of a complex semi-simple group, but of course that has a maximal compact, is the sections of a line bundle on the flag variety. And that line bundle is Neff, that it's only the Neff line bundles on the flag variety. And the point is, well, that line bundle defines a map into projective space. As I say, it's the map that's just projectivized the representation. Well, that embedding also gives me a Kähler structure on the flag variety. And that Kähler structure actually corresponds to its symplectic structure as a coadjoint orbit. So there's sort of a correspondence here of, like, do you think about the line bundle or do you think about the symplectic form that comes from the corresponding Kähler structure?
Sorry, so are you saying that an irrep gives a projective embedding of the flag variety?
Yes.
And there's different ones for different representations. And
well, it's an embedding in a different projective space.
Right.
For a different representation. So yes.
I see. Okay. Weird.
Yeah. Let me. This will be easier to say after I say a tiny bit more here. If what you're used to is the sort of usual highest weight story for representations, what's happening here is your coadjoint orbit is the complexified group mod some parabolic. And the pre-quantum line bundle comes from the one-dimensional representation of that parabolic, which in the usual convention is actually the lowest weight of the irrep. I think I have that right. I'm always a little worried about that, but I think I have that right.
Dare I ask what a parabolic is? I've done a little bit of reading, so I've seen this word before, but I'm just sort of anyway.
Well,
it's okay.
I mean, sort of the lame answer is you define an action of the complexification on a coadjoint orbit, and it's the stabilizer of one of those actions.
Okay.
But the thing to think about in like SUN is its block upper triangular matrices.
Gotcha.
Right. So, the story there is when you have a coadjoint orbit, right? So you're supposed to see in your homework, right, that a coadjoint orbit in SUN corresponds to you have some fixed eigenvalues and you think about all the different possibilities for what the different eigenspaces are, right? And well, the extension from SUN to SLNC is just the obvious one. You let SLNC act by CN instead of SUN. What's the right way to say this? What you're going to get is the stabilizer of a chain of subspaces, a flag, which is why you get a flag variety. So, the block upper triangular matrices, those are exactly the matrices that preserve some flag of subspaces.
Okay.
So the thing I was going to say about Burrell Va is if you have any representation of, let's say, compact group, but actually let's say of its complexification. So I have a representation of GC. So I can look at the projectivization of that. GC acts there as well. There's a theorem that there's a unique closed orbit. So another way to define the parabolic is it's the stabilizer of a point in one of those closed orbits. And this unique closed orbit is actually isomorphic to the corresponding coadjoint orbit as a complex manifold. And this is the embedding that corresponds under the usual connection between projective embeddings and line bundles to the pre-quantum line bundle for your choice of symplectic form. All right, any more questions?
Yeah, I have a question just regarding this correspondence between coadjoint orbits and irrep spaces. Can we use this to understand like why exceptional isomorphisms exist? Like, for example, spin 3 is isomorphic to SU2 and higher dimensional stuff. That's sort of like, I don't really understand the pattern in that sort of isomorphisms for spin groups specifically.
It's not obvious to me why you can do that. Right. I mean, there are various ways of thinking about where those isomorphisms come from, but it isn't clear to me how this would help you.
Yeah. I guess one would hope for like a systematic characterization.
Right. I mean, if you want sort of a systematic explanation of what happens, like I think you're better off like looking at the Dinkin diagrams. Right. Like, I think if like the Dinkin diagrams explain all of these small rank isomorphisms.
Right. That's the only way, I guess. Yeah.
I think that's the best I can do.
Okay. Thank you.
Which is another way of saying, like, look at the actual root systems, right? That like SO3, its root system has rank 1, so like it's got to be the same as any other rank 1 root system. Similarly with the other small coincidences between these guys, right? If you like think about the root system and then like which of the associated groups you're getting, like like spin 3 is the same as SU2 because they both correspond to the root system, which is like one-dimensional and has a Weil group given by Z mod 2Z, and they're both simply connected, right? All right. Well, that's something I'm happy to talk about more, but it's getting a little outside the scope of this course. All right. So we still got a little bit of time. And what I was hoping to do today is just to shut the door on geometric quantization. I'm happy to talk to people more about it. I know it's interesting for people. And the sort of topic I wanted to end the course on, we still have 3 more lectures after this one, is mirror symmetry. This is like a huge topic, so I feel like I'm opening a Pandora's box here or something, but at the same time, like it's such an important part of modern symplectic geometry, I feel like we would be really missing something if we didn't say like a little bit about it. Now, and especially in view of the fact that I only have 15 minutes left, I just want to give a little kind of motivation and overview today. And next Monday, actually, Justin will be doing the lecture because I am busy with various stuff. So he'll probably talk in quite a bit more detail about how this works in a few simple cases. All right. So what's sort of the story? This is, I may embarrass myself trying to explain this, but the very rough idea is back in like the 70s and the 80s, physicists said, oh shit, we don't understand how quantum mechanics and general relativity relate to each other. We'd better figure out how quantum gravity works. And they had various ideas for how quantum gravity might work. And one of the ideas they got was this idea of string theory, that actually you should represent particles not as particles, but as strings moving around in some space. And they thought about the mathematics of that, and it ended up being pretty complicated. And eventually they figured out, well, wait a second, the mathematics of this are only going to work if the universe is actually 10-dimensional. Well, we don't see 10 dimensions. It feels to us like we're living in a 4-dimensional world. So those other 6 dimensions have got to be very small for us to not notice them. And eventually, I think Witten is certainly seen as the key person in this, but there's a paper of Candelas, Horowitz, Strominger, and Witten, which worked out, okay, well, we might be able to get something that looks like our universe. If the universe is 10-dimensional, we have a factor which is the usual 4-dimensional space-time we're used to and we can observe. And then there's a 6-dimensional factor which is extremely small and has a Ricci flat Kähler metric. So they started in the physics and said, okay, we need to have these kind of symmetry properties. We need to have this kind of consistency. And the relation they got at the end is, well, that other factor, it has to have a Ricci flat Kähler metric. All right, well, very luckily, this was in 1985. So like just a few years earlier, Yau had proved that there are manifolds with Ricci flat Kähler metrics. They'd done this 10 years earlier. They might have just said, well, shit, nobody's ever found such a thing. What are we supposed to do? But luckily, Yau had solved that particular problem for them. Yeah. Okay, so suddenly, physicists thought, or at least certain very theoretical physicists who wanted to understand the 6-dimensional other factor of the universe, thought, oh, suddenly Calabi-Yaus are very interesting. But we ended up in this kind of strange world. So they had sort of shown basically, if string theory is really how the universe works, then reality has a factor which is a 60 Calabi-Yau. Which 60 Calabi-Yau? They didn't have an answer. They just said, well, somehow like the things can only work out if it is a 6-dimensional Calabi-Yau, but there doesn't seem to be any particular one which looks better than any of the others. All right, well, so people said, okay, well, how can we make observations out of physical theory which would tell us what Calabi-Yau those 6-dimensionals are, right? This seems like a pretty important physical problem to understand what the structure of the other dimensions of the universe are, assuming that they exist. So if you think about usual space-time, a particle moving around in it, well, so you're thinking about a map of a 1 manifold into that space-time. This is how people kind of, would think about usual classical physics as maps of 1 manifolds into space-time. Well, if you have a string, you don't have a map of a 1 manifold into space-time. You have a map of a 2 manifold into space-time. You end up with a 2-dimensional quantum field theory. And so they sort of said, okay, well, what properties of a Calabi-Yau are we going to be able to read off from looking at maps of 2 manifolds into it and looking at the quantum field theory that comes out of that? And they found a pretty interesting thing that you can read off, which is the Hodge diamond. Now, if you want to explain this properly, you have to go into a bunch of stuff about conformal field theory. But, whoa, that's interesting. Apparently, that was too much for my iPad to try to talk about quantum field theory. Blew things up. Too hot for the iPad. All right, so yeah, I'm going to leave it to some other source for you to learn about conformal field theory. But whatever conformal field theory is, we get one out of looking at strings in our Calabi-Yau. And inside that quantum field, that conformal field theory, is hiding the Dolbeault cohomology of M. Now, there are a couple of wrinkles for how the Dolbeault cohomology of M comes out. One is it does naturally have a ring structure, but it's not the usual one on Dolbeault cohomology. Oops. I have a bad habit of writing cohology instead of cohomology. I don't know what is going on there. It's a deformation of that ring structure called quantum cohomology. And that I think we'll maybe try to talk about next week. We'll see. So that's its own kind of interesting story, but not one we have time to discuss. On the other hand, when you do this process with the conformal field theory, like you kind of make some choices, and these are not like complicated choices. They're they're like sort of some kind of sign convention kind of choices. And if you switch those around, they're things like, oh, do I want this complex structure, or do I want -1 times this complex structure? Those kind of choices, pretty arbitrary seeming things. And if you make those choices differently, you get a different Hodge diamond. You get a Hodge diamond that's reflected, so that because of the symmetries of the Hodge diamond, it doesn't matter whether you're reflecting through the northeast southwest line or the northwest southeast. But if I reflect through either one of these lines, I get a totally different Hodge diamond. So one example we had talked about had a Hodge diamond that looks like this. I feel like I'm putting too many things in this Hodge diamond. So I'd be flipping the 1s and the 101s. All right. So somehow, out of almost the same physics, so I just looked at with a slightly different perspective, I could get this very different Hodge diamond. Not that different, just reflected. And the appearance of this reflection led to the name mirror symmetry. With the idea that the same physics might come out of two different Calabi-Yaos whose Hodge diamonds are related by this reflection. This just seems to be what the physics tells you might happen. And at least when this was first noticed, there was just, well, hey, like, we could do it this way and get this Hodge diamond. We could do it this other way and get this reflected Hodge diamond. Well, I wonder if Calabi-Yaos come in pairs such that we get these two different Hodge diamonds out of them. And, well, people worked examples, and they kept finding examples of pairs of Calabi-Yaos that have exactly this relationship. The Hodge diamonds are reflections of each other, and there are lots of other things going on. One of the most basic is somehow stuff involving the complex structure on one of them involves the symplectic structure on the other one. So in this case, the symplectic structure lies in this piece of the Hodge decomposition in H11, since it's a Kähler structure. So these guys are telling me something about the symplectic structure and how I could deform that, whereas actually these guys are telling me about how I could deform the complex structure. But this is still not as well explained as it should be. And sort of why Calabi-Yaos come in these pairs. And at least at first, it was just kind of an observed fact. They see these pairs exist. Isn't that an interesting observation? And it's sort of gotten more and more evidence over the years has piled up that this is a real phenomenon. So, as I said, what I want to sort of end this class on is a little discussion of what's the actual relationship between these mirror pairs, and where does it come from, to whatever degree we can explain it. All right. That's my rough introduction to mirror symmetry. And Justin will get more into the nitty-gritty on Monday. Are there any questions?
Will you be talking about 2D or 3D mirror symmetry?
This is all 2D.
Okay.
I'm happy to talk to you about 3D mirror symmetry, but I think that's outside the scope of this course.
Okay.
Maybe a little bit in that course in the fall, but there won't be time for much. But yeah, this is all about so the physics term here. This is all about 2D n equals 2,2 theories, 2D theories with n equals 2 supersymmetry. And so I started enjoying writing this with a red 2 and a blue 2. Oops, not a blue 3, a blue 2. And the mirror symmetry is about swapping the two 2s. So the one way to say sort of what the change is that flips these two things is changing the roles of those two 2s. All right. Any questions?
I have a question.
Yes.
You mentioned that the ring structure on the cohomology that shows up is not the usual ring structure, but rather quantum cohomology.
Mm-hmm.
Is that the explanation of the quantum in quantum cohomology, or?
That's an interesting question. I can't definitively say yes, because sometimes people just throw the word quantum onto things to like explain, like to just mean that it's deformed.
Right.
But I suspect so. I don't think people had really thought about quantum cohomology before this story.
But the deformation, in fact, is something that you can do. Like the deformation doesn't depend on the fact that you're working on a Calabi-Yau or something, right? Like you can, I mean, you do quantum cohomology of all kinds of things that are not Calabi-Yaus.
Yes, that's certainly true.
But it's the same. It is, you know, the deformation is somehow, it's deformed in the same way, or there's some, is that?
I mean, somehow the thing that's different about being Calabi-Yau is, I mean, so if you start with something that isn't Calabi-Yau, yes, you have the quantum cohomology. And in fact, like now there's a lot of stuff about mirror symmetry for non-Calabi-Yau things. But the point is, like, if you're not Calabi-Yau, then your mirror isn't like a manifold, right? You know, a variety, it's some other object. So somehow, like, the thing that's nice about Calabi-Yaus is if you're a Calabi-Yau, then your mirror should just be another Calabi-Yau. Whereas if you're not Calabi-Yau, then it's some crazy Landau-Ginzburg model.
Okay.
So, or, you know, I don't know. Some people really like Landau-Ginzburg models, but you know, it's something genuinely different on the other side.
Okay. Thanks.
But yeah, I mean, somehow you should actually think about this. I think that the quantum cohomology is really just an invariant of the symplectic structure, and so this becomes a story about like stuff involving the symplectic structure on one side is expressed in terms of some other stuff involving the complex structure on the other side. All right. Any other questions?
Will Kontsevich's ICM be mentioned?
Probably mentioned, yes. Yeah, no, we'll see. We'll see exactly how much I feel I can get through discussing, but yeah, I mean, like homological mirror symmetry is definitely one of the things I want to say a little bit about. I mean, in part because, right, like we we definitely don't, you know, I don't want to go down that kind of like conformal field theory direction. So, you know, what can we discuss? Like, I don't know, I feel like one of the things we should like discuss at least a little bit is the Fukaya category. And to explain why we're doing that, like the reason is Konsevich's ICN, right? All right. And, you know, if there are particular things people would particularly like to cover, you're free to let me know. I mean, you know, I will be limited by kind of what my expertise is and what sources I can find, but I'm happy to have input on what people would like to hear about.
Floor theory.
Well, yes, so I mean, when I say the Fukaya category, I'll have to say something about floor theory. That's a particularly kind of deep rabbit hole to do in real detail, but it's worth saying something because yeah, it's a really important part of modern symplectic geometry now. So I think completely skipping it is you know, giving the field short shrift.
I just have a question about it's not related exactly to something that you were that you said. I just wanted to ask something about this the method of coadjoint orbits. But if other people have more specific questions, I can wait.
No, you can go ahead.
Yeah, because it's just I was reading about in Kirilov's notes, right? I was reading about he does this, which you also talked about, and he talks about how okay, you start basically if you have, let's say you have a coadjoint orbit, which is a single point, so that's like an element of the dual of the Lie algebra, then that defines a one-dimensional representation of your group. And then he says, okay, so if we want to look at a more general situation, like a larger coadjoint orbit, I think he was my interpretation was like he was saying like, okay, you can pick a point in the coadjoint orbit. You can look at a group that stabilizes that point, and then you of course get a one-dimensional representation of that. And then to get the representation of the whole group, you use induction. And my question was, so I was a little confused by what an induced representation in this infinite dimensional situation would look like. Like if you have a one-dimensional representation, and he writes this formula where he's like, okay, you have you can look at all of the elements of the coadjoint orbit for the big group that project down to a particular element of the coadjoint orbit for this, you know, as a subgroup, you know, like and then he writes some integral over the points in this larger orbit, which is like, what is this integral? I didn't understand what he meant by that. Like he doesn't really explain what he means by
well,
you know what I'm talking about?
Probably, you know, probably he's thinking of sort of direct integral. So what does that mean? Like, okay, so how, in this language, how would I talk about this like Burrell Va construction? So yeah, I have my compact group. Inside that, I have a maximal torus. And I have a representation of that maximal torus on some one-dimensional complex space, right?
Yeah.
So, you know, the way I would interpret induced representation is the vector bundle on G mod T. So there's a line bundle on G mod T induced by this guy. By thinking of G as a principal T bundle and taking the associated vector bundle for this representation of T.
Oh, I think I see what you're saying.
And so
Oh,
a section of this bundle is essentially choosing an element of all of those spaces in the induction. So somehow you should think of the induction as sections of this line bundle.
it's like the fibers are the cosets.
Yeah.
And it's like I see. Okay, because I'd seen
now-
induced representations for finite groups, and I was like, what's the uncountable direct sum over coset representatives of some subgroup? And like, oh, it's just a bundle of coset. Yeah. Okay.
Right. So in fact, it's true that the induced representation is the sections of the associated bundle on the coset. Like that's the right way to think about induced representations, even for finite groups.
Yeah. No, it makes sense. Yeah.
Now, in this case, I then say, oh, but I have this geometric quantization story. I don't want all sections of this line bundle. I only want holomorphic ones. And that gives me the finite dimensional representation. So in that sense, the finite dimensionals are induced from the torus.
Huh.
I have to put in that holomorphic restriction.
You need to talk about how. So one thing, yeah, that's interesting, huh? And that's Burrell Va, or that's like
That's Burrell Va.
Very interesting. So where does this holomorphic come from if we're just talking about symplectic manifolds? Is it
It's
the
polarization.
Kähler polarization? Is that the place where it comes from? Just the Kähler?
Yeah. It's Kähler polarization.
Interesting. What if you have a real polarization instead of just a Kähler polarization?
Well, I mean, of course, these guys don't have real polarizations.
I see.
Like it's impossible topologically.
Okay. Well, that's helpful then. Don't have to worry about it if it's not possible. Okay. Cool. Very cool. Thanks.